Hello everyone. We're going to work through another example here today. This will actually be our last recursion tree example. This is about as hard as these problems can be made for a class like this. So here we have a lopsided recurrence. We have one recursive call of size n over 2, a second recursive call of size n over 4, and our additional cost is Cn. So let's get right into it. To analyze this, we start with the cost of the first recursive call, which is Cn. It then forks into three different problems, one of size n over 2, and two of size n over 4. So just to let myself keep track, somewhere I'm going to denote that the red path is for dividing by 2, n over 2, and the blue path is for dividing by n over 4. So I'm also going to try and keep track of the level somewhere. The level I'll do in black over here. At the root we have level 0, and then at this next level we have level 1. We could try to keep track of the size of the problem, but that tends to be very difficult when we have two different sized recurrences because there's not a nice way to notate that. So we'll just deal with what's happening. So to the left, we have a recursive call of size n over 2. Plugging n over 2 into our additional cost, we get Cn over 2. Plugging n over 4 for the blue branches into our additional cost, we have Cn over 4 and Cn over 4. Each of those three processes will generate three more processes. Each will generate one of by dividing the problem size by 2, and 2 of dividing this problem size by 4. So, on the far left here, I have a problem of size n over 2 that I'm cutting in half, so I get a problem of size n over 4, and we plug that into the additional cost, and have Cn over 4. For the blue lines, I have a problem of size n over 2 that I divide by 4, so I have a Cn over 8 there, and a Cn over 8 there. For the middle branch, for the red path afterwards, I'm taking my problem of size n over 4 and dividing it by 2, and getting a problem of size n over 8. Then the two blue branches, I'm dividing it by 4, so I'm getting problems of size n over 16. And the far right branch there is the same as the middle branch, so we have Cn over 8, Cn over 16, and Cn over 16. We keep doing this until eventually one of these branches terminates. Which one's going to terminate first? Having the problem or quartering the problem? It's going to be quartering the problem. So actually, any branch that's just blues will end first. So we're going to keep going until eventually this blue branch terminates over here. We're going to cut off the tree there. This red branch on the other side will keep going for some time until eventually it terminates. So the first of the branches that terminate is the ones that are taking nothing but the n over 4 path the whole way through. Now, let's compute the cost at each level. The cost for the base level here is Cn. The cost for the second level, the first level, is going to be Cn over 2 plus Cn over 4 plus Cn over 4. That gives us Cn still. This next level looks really messy. I have one copy of Cn over 4 plus 4 copies of Cn over 8 plus 4 copies of Cn over 16. Adding those up, I get Cn over 4 plus Cn over 2 plus Cn over 4, which is still just Cn. So the cost for that level is Cn. And if I notice the pattern of Cn, 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 this will keep happening for all of the levels until the first branch terminates. So the cost at each level is Cn. We have level 0, level 1, level 2, and then eventually we will terminate down here. in order to bound this from below, I must determine the length of the path that terminates first. In this case, that's the rightmost path. So I must determine how long this path over here is. We denoted that before with k, and we will do the same thing here. So we must determine when the first path terminates. So that's when we were continually dividing by 4. So what we have to solve here, must solve. When does n over 4 to the k equal 1? Well, that happens when k is equal to log base 4 of n. So the number of levels there is going to be log base 4 of n. To compute the cost of taking nothing but the blue branches, the cost of doing that, we're going to pretend to cut off the tree at the orange dividing line. If I'm pretending to cut off the tree at the orange dividing line, then I am bounding it below, because I'm ignoring some of the nodes in the tree. So t of n had for sure better be greater than or equal to cutting it off at the orange line. If I'm cutting off at the orange line, well, the cost of each level is cn plus cn plus cn, a whole bunch of copies of cn. How many copies? Well, there's one for each level of the tree that I'm paying attention to. How many levels are there? There were log base 4 of n levels. So t of n is greater than or equal to cn times log base 4 of n. That lets us claim that it is in big omega of n log n. So let's draw that conclusion. Therefore, t of n is in big omega of n log n. So hopefully we can show it's also in big O of n log n, in which case we'll be done. Now, in order to bound it from above, what we must do is bound the cost at each level. So I can bound the cost of all of the levels below the orange line by continuing to extrapolate the pattern. So all of these costs have to be less than or equal to continuing the pattern, because there are fewer nodes being considered than we were above the orange line. We now have some of the paths terminating. So everything below is less than or equal to cn, all the way until the furthest down node in the tree. So we still have to compute the height of the tree, h. We still need to determine that, which we determined similarly to how we determined the height of the subtree we looked at over there. So we must solve n over 2 to the h for the height of the tree is equal to 1. Solving that for h, we get h equals log base 2 of n. So we know that each of the costs is less than or equal to cn. So t of n is less than or equal to cn plus cn plus cn plus having a cn for every single level of the tree for the entire height of the tree. What's the height of the tree? Well, we just computed that. That is log base 2 of n. So t of n is less than or equal to cn times log base 2 of n. So now we can draw the conclusion. Therefore, t of n must be in big O of n log n. If it's in big O of n log n, and like we showed before, it's in big omega of n log n, it must be in big theta of n log n. So, as a final conclusion, t of n is in big theta of n log n. This problem is not much harder than the previous one. We just need to be careful when drawing the tree. The only ways that this problem can be made harder is if finding the pattern across the levels is made more difficult. But the only difference that happens there is what we write down in the final steps and how we identify the pattern. We did not do that here, but that may be possible to see in the future. But other than that, this example is very similar to the other examples we have seen.